I forgot to start recording. So let's find out what happens in a nozzle. I'm going to jump over to my document camera. Let's get it on. All right. So let's play our usual game here, meaning mass, momentum, energy, because they're always conserved, right? Giddy up. So one thing to remember as you start into this is that prior to now, we've been thinking of 1D flow. Actually, I think I might have this on the slide. Oops, no, I don't. Okay, well, I have it here. So when we looked at our shock waves, so there's our normal shock. We drew there's our normal shock. We drew a control volume like this, right? So the area that the flow entered and left by was the same. That's 1D flow. So you might have different conditions on each end, but the inlet area and the outlet area are the same. That's 1D flow. Effectively, we're taking that. Oops. Just threw that out. Oh. I dropped it and I can't find it anymore. Oh, there it is. Effectively, we're taking this and we're saying, well, we have a nozzle, right, or a diffuser. We have something where that second area is going to change. It's not going to be equal to what it was at the start. So taking this, saying forget about that. Next. So our model looks a bit more like this, where you have some inlet conditions here. Et cetera, et cetera, et cetera. And the inlet area does not equal the outlet area, which is called, and definitely not 1D flow, because if I follow going from the inlet to the outlet, it's going to be something like that, right? And there's definitely motion that's not linear there, right? It's in more than one direction. However, what we're going to do here is assume quasi 1D flow, because it helps our analysis. So, what's quasi 1D flow? We've seen this before when we looked at helicopter aerodynamics briefly, right? In quasi 1D flow, we assume that the majority of the momentum is in the same direction. And any momentum changes occur in that same direction. We also, as a corollary, we say all non-1D velocity or momentum is small. So like when the flow curves that way, in order to expand, we assume that it does that the amount of momentum in that direction is small, which is not a bad assumption. I mean, relative, if you're going to Mach 3 out of a nozzle or whatever, or Mach 2 out of a nozzle, it's probably not going Mach 3 that in a direction perpendicular to its direction to the X of the nozzle, right? That makes some intuitive sense, does it not? So it's not a bad assumption to make. As a result of this assumption, though, we're going to neglect all velocity components that are not in that direction, that are not parallel to the axis of the nozzle. So we're going to ignore, if not parallel to the nozzle axis. Nozzle axis being something like that. Just a center line of the nozzle. So, with that in mind, if I take this away, mind if I take this away, Ian? Okay, sounds good. It's a set. So, with that in mind, if we write out our expression for the conservation of mass, we know m dot in has to be m dot out. Whatever mass you put in has to come out. So the mass flow rate into the nozzle has to be the mass flow rate out of the nozzle. You know, mass flow rate is what? What do we define mass flow rate as? Still there? You still there, Ian? Ah, got it. Thank you. All right. Thank you. Pretty much, it's close to dynamic velocity or dynamic pressure. It's just rho u, right? Rho u times area. So, Q is rho. Got it. So prior to now, when we've said mass flow rate, we've always been able to say areas are the same, right? That's why it was rho u. Now we can't say that areas are the same. So we have to say density times velocity times area at state 1 is density times velocity times area at state 2. That is that's now our expression for conservation of mass through a nozzle. All right. That's a conservation of mass, but we'll get too far. Just for reference, on the slide, I've put up a sketch of the control volume that we're looking at. Essentially, just takes this, it makes it look pretty. So there you go. Note the walls of the control volume, the ones at the top and bottom. We're defining those to be streamlines because the streamlines, there's no flow perpendicular to them. That vector ds that you see on the bottom there, that's an area vector. So it's just taking a chunk of the control surface there, meaning the edge of the control volume, and showing you an area vector, which is by definition perpendicular to the wall of the control volume. So, just give you a second to write that out if need to. Okay, so now that we did conservation of mass with that, let's do conservation of momentum. So, assuming inviscid flow with body forces, no gravitational, electromagnetic forces, etc. Irrotational flow and steady flow. A flow that is inviscid, irrotational, steady, and without body forces. Our expression for the conservation of mass, or sorry, conservation of momentum, looks something like this. Okay, so this over here again, which we said, well, that's kind of like momentum before, right? That's like an area. That's like a speed again. So it's like momentum that's parallel to your area vector, and because the area vector is pointing straight out of the control volume at all points, it's like momentum that's entering or leaving the control volume. This is like pressure acting on an area. So let's have a go here. So rho u dot ds. Where is that equal to 0? Where is the momentum perpendicular to the area vector? Excuse me. At state 2, so at the exit there, right there along this line. Okay, so dx here is always perpendicular to the side of the control volume. So if I was to draw it, always perpendicular to the wall, right? So up here it would be like that. And at the inlet, it would be like that. The exit would be like that. The flow at the exit is actually parallel to the area vector ds, as it is at the inlet. But what about along the sides? So from here to here and here to here, by definition, we're saying that these sides of the control volume, these control surfaces, are streamlines of the flow. So what does that mean for our flow's velocity vector relative to the area vector ds? What direction are they pointed in relative to one another? Yeah, it's called, by definition, the velocity on a streamline is perpendicular to a direction normal to that stream. This flow is always tangent to the streamline itself. So here and here, the flow is perpendicular to the area vector, which means the momentum is perpendicular to the area vector. So rho u dot ds, if we go back to the document camera, this guy is going to be 0 for the upper and lower sides of the control volume. However, at the inlet and the outlet, U is parallel to S. So the dot product of them is just rho 1, U1, A1. And if I follow my thing here, I also have to multiply by another U at the end. So I get that. And I'm doing the integral, so it's state 2 minus state 1, right? So that's state 1, negative, plus state 2, or 2, U2 squared, A2 equals. That's my left-hand side. Okay, now my right-hand side, this one's a little bit more interesting. It's just P dot ds. So it's some pressure multiplied by an area. So the inlet and the outlet are relatively straightforward, right? I just have some area and I have some pressure act on it. So like that, right? Sorry, it's negative. Plus P2, A2. But there's also pressure like all around the control volume, right? So there's some pressure acting on the acting on the upper and lower surfaces of the control volume as well. We don't know what that pressure is, nor do we know what the area is. So we're going to express it just as an integral from the inlet area to the outlet area of P dA. And that's our expression for conservation of momentum. Woo. All right. So that gives us mass and momentum. Now for energy. Onwards and upwards. So again, we assume that we have inviscid, adiabatic, flow with no body forces. And if we assume all those things, our expression for the conservation of energy starts out looking something like this. Where E is your internal energy per unit mass, U is your velocity, S is your area vector, P is pressure, rho is density. So we got all that, and we can do the same kind of analysis that we did before. Throw it at our control, see what's parallel, what's perpendicular, and we'll get something that looks vaguely like this. Where I'm just going to, U1's just a magnitude, so I'm going to drop the magnitude sign. keep in mind that this is multiplied by this guy. Those two terms are multiplied by each other. And you can simplify that puppy down, get it to look something like a thing that could be vaguely useful, or this. Which is an expression for the conservation of energy, but there's a couple of terms in this. So let's see if we can knock it down. Okay, I'll just give you a few seconds to write that down. Okay, so if we take all this equation and want to try to simplify it, one way that we can do that is by dividing through by our expression for the conservation of mass, because there's rho u floating around a bunch here. We got a bunch in conservation of mass. So let's divide through by the rho ua equals rho 1 u1 a1 equals rho 2 u2 a2. Remember, we divide left-hand side by left-hand side, divide right-hand side by right-hand side, and we get something that'll look a heck of a lot like this, which is much more appealing. Heck of a lot more appealing. And if I remember my definitions, this is like enthalpy. So I can even rewrite this as that should look awfully familiar from all the stuff that we just did in isotropic flow, right? Like that was our energy equation for a calorically perfect gas. One more assumption. All right. So a consequence of this equation, or something that will pop out of this, was let's see, what was that? Or rather, with this, when we use this equation for isentropic flow and all that, what happened to our stagnation enthalpy or our stagnation temperature? Did they change at all? So could we say that they remained constant anywhere in our flow field? Yeah. So because we're using the same expression, means that that would be the same here too. So which shouldn't surprise us because we assume inviscid adiabatic, right, which is isentropic flow in our case. So because we're looking at isentropic flow here as well, we also should expect stagnation temperature to be constant and stagnation enthalpy to be constant. So assuming, of course, that we get any shock waves, which is kind of a big assumption. It's possible, but it's something that we have to also list. We have no shock waves because as soon as we get a shock on this, that assumption of isentropic flow goes away, right? Because shock waves are entropic. So the way to do that is to change the shape of the nozzle gradually. So long as we do it slowly and smoothly, you can generally avoid shock waves, which is how they make like supersonic wind tunnels and such. So it is something possible. It's just not necessarily going to happen for like a jet fighter or something like that. So another assumption I have to list. So anyway, we have a bunch of equations that we can play around with now. So let's see if we can start going after that change of area and change of speed thing that we kind of first talked. So we're going to take our expression for conservation of mass, and we're going to differentiate it. Now I'm going to test here. In order to work out the math to the form we want, you need to use calc that, to be honest, I fully understand. I think it's called fractional calculus. So we're just going to accept the result of other folks who have done the math and go forward from there. You do that. You get an expression. You can hammer it into an expression that looks something like that. And we want to solve for how do I say this? We want to try to solve for area and velocity, right? So we want to try to eliminate this d rho over rho term eventually. We have to figure out how to do that. So one thing at a time. So first thing that we can do is that if we look back at some previous work that we did, we can say, well, we know that density and pressure are related to velocity by way of Mach number. So if we do some manipulation in there, we can come up with a separate expression that kind of relates density and pressure, because we know that d rho over rho times dp d rho gets us this dp over rho, which if I equate it to Mach, if I equate it through the speed of sound rather, and Mach number to velocity, can get me this kind of a relationship. We also know that this is I'm going to say this, that this relationship can be is only true for isentropic flow. So again, just keep in mind adiabatic and viscid isentropic flow here. So if we take this, we say, okay, this dp over rho thing. Well, if I can, I know that the speed of sound, a, c, whatever variable you want to look for it, that's like gamma rho t, or if I use my ideal gas law, it's like gamma p over rho. Well, if I take a derivative of this, which I did when I was trying to get this in the first place, I can say that dp d rho is actually equal to the square of the speed of sound. So if I take that, I shove it back into here, I can get something like, oops. I can get something like that. And as a result of that, if I, hang on, make sure I'll make sure that I'm doing this correctly. If I divide through by a squared and take out a u, so I'm just going to multiply by u over u. So that effectively gets me d rho over rho equals negative u squared over a squared du over u. U squared over a squared, that's like Mach number, right? So if that's all true, if I can pop over to this guy and just substitute that back in here. So get something that looks like this. Which now is only in terms of velocity and area, which is what I wanted. So if I just solve this puppy down, I can get something that looks like that. This what's called our area Mach number relation. So let's do some thought experiments here. Keeping in mind that dA and du are changes in area and changes in velocity. If I have a, how do I say this? If I have a subsonic Mach number, so a Mach number less than 1, this term will be negative, right? I have a Mach number less than 1. So I'll just write on the same thing. So if m less than 1, all that is negative. If that's negative, let's say we have let's say that we have a negative change in area. So we go from a larger duct, a larger opening to a smaller opening. Have this Mach number is less than 1 coming in here. If dA is negative and Mach number less than 1, that means that du has to be positive or negative in order to make all the signs work. Exactly. Du has to be positive, which jives with how we think of subsonic nozzles, right? You crank down at the exit, and for a subsonic inlet velocity, you get an increase in speed. Cool. That's awesome. And by corollary, if I go the other way, so Mach number is still less than 1 at the inlet. We now have a positive change in area. in order to satisfy signs, right, because dA is positive now, now in M1 and M is still less than 1, so this term's still negative. So U has to be negative. So we get in. So if we pull our nozzle back apart, we get a negative change in velocity, which again is what we expect for subsonic flow. Let's try this again. So if we have, let's rewrite our area Mach number relation here. Sign, I promise. Du over U. Have my diverging. This is a diverging duct. That's another word for it. Duct just being a bit of internal whole volume that flow is going through. We're going to say we have Mach number greater than 1, which means that this term is positive. This whole thing is positive. This whole thing is positive. We have a positive change in area. So what does that mean about our flow velocity? What's how does it change? What is the sign of du through this duct? Yeah. So du has to increase as well. So that means that for supersonic flow, increasing the area actually increases your flow speed. And by corollary, Mach number is greater than 1 here. I have a negative dA, decreasing the area of my duct. This is a converging duct. Also means I have to have a negative change in velocity. So in supersonic flow, the behavior is opposite subsonic flow, something that we already talked about. Now we have a relationship that kind of shows it a little more explicitly. As a result, this is what's called this would be our supersonic nozzle. In subsonic flow, it would be the opposite, right? In subsonic flow, this would be our nozzle. In supersonic flow, that's our nozzle. And these, where velocity goes down, are what are called diffusers. So nozzle speed goes up, diffusers speed goes down. All right. So now that we got all that, all my notes a little bit. What if you start sticking these things together? So your typical rocket engine does something like this. Where it's a converging, diverging nozzle. The entire purpose of this nozzle is to increase your flow speed, right? So you have flow come in here, and it leaves here going super fast. So you have a converging section and a diverging section. And it's all built to make it go faster. So in order for it to make your flow always going fast, always go faster, what has to happen at this, in the center of the nozzle between the converging and diverging sections? Assuming, of course, that we have subsonic flow going into it. What has to happen in the middle here? Does the Mach number have to hit a certain point? What's going on? Yeah, so the Mach number has to increase through this section. We know that's true because it's a converging sonic nozzle, a converging subsonic duct to the subsonic nozzle. But in order for this to act like a nozzle, the diverging section, the flow has to be supersonic, right? So this throat, that's what this region is called. In this throat, the flow has to go through Mach 1. In other words, we're taking the sonic flow here. We're accelerating by bringing the area of the nozzle down. Then as soon as we get to Mach 1, we can start opening that area up again, and now we're a supersonic nozzle. So the flow here is much greater than 1. So that's kind of the scheme of a converging diverging nozzle, where something can take subsonic flow on the inlet and spit out supersonic flow on the outlet, just by kind of doing this playing this geometry game really, really well. So next week in our last class, try to hold back your ears. In our last class, we're going to talk about this a little bit more, come up with some relationships between area and Mach number that are a little bit more explicit, and see if we can't compute performance of these nozzles, compute properties as we move through the length of the nozzle. The fact that our flow is utterly isentropic will help us, because all of the analysis that we did before with isentropic flow, it still works. So we can still use all of those relationships. All we have to do is factor in this change in area gig, and remember that the behavior of our nozzle is going to fundamentally change around the throat. So, unless you have any questions, that's all I got for today. Any questions, Ian? All right. See you next time. Thanks for stopping by. I hope that you get your mic fixed.